Okay. Similar. If you recall, similar shapes is like a model car. Everything is proportional. Everything is the size it should be in rate, in comparison with everything else. But you can't sit in it. All right? Because I think Sam Bauer said earlier, your model cars that you make are 1/18 the size of the real thing. Whenever an architect designs a building and he's going to come and he's going to show it to whoever wants to build this thing, they will make little models of what the building's going to look like. Have y'all ever seen those? Yes. Mostly on movies, okay? Now, everything has to be proportional and to scale. So if, say, their building is 1/100th of the original size, what does that mean? It's 100 times smaller. It means if you take the height of the building, the real one is going to be that times 100. If you take the length of the front of the building for the model, the length of the real building is going to be that times 100. Okay, so it's a scale factor. Well, we've dealt with scale factors in similar polygons before. Here, these two right triangles are similar. You can find the scale factor by simply comparing two corresponding parts. For instance, I could compare hypotenuse to hypotenuse, or vertical leg to vertical leg, or horizontal leg to horizontal leg. But in each case, what do you get? Same thing, 1/2. 4 to 8 is 1 to 2. It reduces to 1 to 2. 4 square roots of 2 to 8 square roots of 2. How does that reduce? Okay? So every corresponding piece has the same scale factor. So in this one, our scale factor between these two triangles is 1 to 2. Now we're going to do a little experimenting to be able to see, well, how do the perimeters compare? And how do the areas compare to help us see where our theorem that we're going to present today comes from? And this is, let's do this first. Our small triangle and our larger triangle. First thing I want you to do is find the perimeter of each. You can use your calculator and round your decimals to the nearest hundredth.
I just recently forgot how you find the perimeter of a triangle. Yeah.
Just add the sides. You should get 13.66 for the small triangle. And 27.31 for the larger triangle. What's the scale factor of those two numbers? 1 to 2. It's a little off because we rounded. But 13.66 times 2 is 27.32. We're 1/100th off because of rounding. It's like the whole building about to collapse. All right. So let's think about this for a second. The scale factor of a corresponding side and the scale factor of the perimeters are exactly the same. Why would that be?
Because the whole triangles are similar.
Because the triangles are similar, and we're simply adding numbers together and comparing them to their corresponding numbers added together. And since it's just a sum, then it's exactly the same. So here's the first part of our theorem. In similar polygons or shapes, replace that word with shapes, because it encompasses more than just polygons. You got circles, you got whatever. The ratio of the perimeters of the two shapes is the same as the scale factor. And remember, your scale factor can be found by simply comparing two corresponding parts of the two shapes. So in this case, I have a smaller triangle drawn with a height of A and a larger triangle with a height of B. Well, the scale factor of the two triangles is A to B, which means the ratio of the perimeters is also A to B. Very, very simple. So what does that mean? If this is 3 and this is 7, what's the ratio of the perimeters?
3 to 7.
3 to 7. And that can help us to find, for instance, if we knew the whole perimeter of this triangle, but we don't know all 3 sides, then we could find the whole perimeter of the larger triangle because of that scale factor.
Let's say that the length of the hypotenuse is like 5. So you do 3 to 7 equals blank
You'd
to
set
5.
it up as a proportions.
Okay.
Yes, exactly. All right, now let's come back to our two triangles. Now we're going to find the area of each one. Which I want to change my numbers because it can be fooling you, kind of, sort of. Let's change this to, hey, we can't. Hey, never mind.
We'll take you
All right, well, let's just go with this. We'll just do it. All right, find the area. Oh, look. Larger.
Man's dying over here.
Okay. What's the area of this triangle?
16. 8.
Divided by 2. Base times height divided by 2. So it's 8. What's the area of the larger one?
32.
64 divided by 2, which is? All right, reduce that. What does 8 to 32 reduce to?
1/2.
1 to 4. Okay. Now, how do you get from 1 to 2 to 1 to 4? Now, you have to do the same thing to both things, like to the 1 and the 2.
Times 2.
No, because 1 times 2 would give you a 2 right here. How about times itself? Because 1 times 1 is still 1.
So you're squaring it.
And 2 times 2 is 4. Exactly. What is area? What do we always put on the back side of area?
Square.
Square.
Inches squared. Feet squared. It's 2 dimensionals. It's square footage. Square whatever. So, the second part of our theorem says that in similar shapes, the ratio of their areas is the square of the scale factor.